Now, let's try to take the equation that we have derived earlier that relates between pressure and VRMS. Let's take this equation and further manipulate them to find other equations that relate between macroscopic properties of gases and the microscopic behavior of gas molecules. So first you have your pressure and your root mean square speed, which is VRMS, and through the 25 minutes video that I've done earlier, we already obtained these two equations here that relates between pressure and VRMS. Now I'm going to take this equation and further manipulate them to relate between pressure and translational kinetic energy. So translational kinetic energy is basically kinetic energy that is associated with the translation of an object. So translation here basically means the motion of object across space. So if you learn mathematics, there's a motion along the x-axis, motion along the y-axis, and motion along the z-axis, or we call it as IJK in maths or engineering. So translational kinetic energy is energy associated with that kind of motion. Okay, so to do this, to find the equation that relates between pressure and translational kinetic energy, or KTR, I'm going to recall back an equation that we are most of us familiar with, okay, which is kinetic energy is equals to half mv squared. But for this situation, because kinetic energy here is related to the translation of the molecule, so it's KTR, whereas the V here, we are going to replace it with the root mean square speed because that's what relevant to a gas system over here. Okay, so we have the equation PV is equals to 1 over 3 Nm VRMS square. So what I'm going to do is we can see that there's a similarity here between mv square and mv square over here. So what I can do is we can manipulate the equation by changing it to half mv square. So because we change it to a half mv square, we have to times 2 over here. So this 2 and 2 will cancel back out, then you come back to this equation. Okay, it's just mathematical manipulation. But from here, you see that half mv square here is equals to KTR, so we can replace it with KTR. Okay, so now you've derived an equation that relates between the pressure and also the translational kinetic energy, KTR. Okay, very simple manipulation. Basically, take the previous equation, use what we have, use the knowledge that we recall, and combine the two equations to get a new equation. Okay, now we further manipulate the equation by relating between translational kinetic energy. We're going to relate it with temperature. Okay, translational kinetic energy relates to the microscopic behavior of gas molecule. This is a microscopic property, but temperature is a macroscopic property. And so you can see macroscopic things are labeled in pink, whereas microscopic things are labeled in green. Okay, so what knowledge are we going to recall in order to manipulate this equation further? We are going to recall our ideal gas equation. So there are two versions of ideal gas equation in our syllabus. One is the molar version, the PV is equals to nRT. One is the per molecule version, which is PV is equals to nKT. So we take this equation PV is equals to nRT, and we are going to combine it with this previous equation, PV is equals to 2 over 3 nKTR, replace it with nRT. Okay, yeah, we combine these two equations, 2 over 3 nKTR is equals to nRT. Now we are going to manipulate this equation by bringing the 2 over 3 to the other side, making it 3 over 2 nRT. Okay, I want to bring your attention to the left-hand side of the equation over here. Left-hand side of the equation, this KTR here is the translational kinetic energy of one single gas molecule. So if you take the kinetic energy of one single gas molecule, you multiply by the total number of gas molecules that are there in the gas system, what you're able to get here is actually the total translational kinetic energy that we have in the system. So let's imagine if you have 10 molecules in the system, each molecule has 1 joule of kinetic energy. So 10 multiplied by 1, you get 10 joule that represent the kinetic energy of the whole gas system. Okay, so we can replace this nKTR over here with KTR total. And because of that, KTR total is equal to 3 over 2 nRT. And because we know that nRT is equal to PV, PV is equal to nKT, we can replace this nRT with nKT as well. So you have your equation for total translational kinetic energy of the gas system. Okay, if we use this equation to manipulate and combine it with the previous equation, you have your PV is equal to nKT. You replace the PV here with 2 over 3 nKTR. So now you can see that the n on both sides can be cancelled, and you can bring the 2 over 3 to the other side to become 3 over 2. Then you get your another equation, which is translational kinetic energy for one single gas molecule is equals to 3 over 2 Boltzmann constant times the temperature. How is this equation on the right different from the equation on the left? The equation on the left here represents the translational kinetic energy of the whole gas system, which has many gas molecules inside. So you take one single gas molecule's kinetic energy multiplied by the total number of gas molecules in the system. Okay, so this is total translational kinetic energy of the whole gas system. But this equation on the right here is the translational kinetic energy of one single gas molecule only. And they differ by a single value, which is the big N over here. So you can see it's multiplied by big N, you get total translational kinetic energy. Okay, so we have already manipulated 75% of our cycle over here. The last step will be to relate between the temperature and the root mean square speed. So again, temperature is a macroscopic value, whereas root mean square speed relates to the behavior, microscopic behavior of the gas molecules. Okay, so what concept are we going to use to relate between these two quantities? We are going to use back translational kinetic energy. K is equals to half mv squared. Again, V for gas molecules, they are all in different speed, so we represent it with root mean square speed squared. Okay, so we are going to manipulate the equation by using this KTR total is equals to 3 over 2 nRT. You are going to break the KTR total back to N multiplied by KTR, then KTR can be replaced by half mv squared. Okay, I'm going to replace this big N over here, which represents the total number of gas molecules, with the number of mole multiplied by the Avogadro number. So if I have 5 mole of molecules, each mole has 6.02 times 10 to the power 23 molecules, I can get how many gas molecules in total do I have. Okay, it's a simple relation. Maybe I can write it down. The number of mole is equals to the total number of gas molecules divided by the Avogadro number. So from here I can see that N is equals to number of mole multiplied by the Avogadro number. Okay, so a simple manipulation of this capital N over here, then the KTR translational kinetic energy, we break it to become half mv squared. So once we break it already, you can see the 2 can cancel out, the number of mole can cancel out, then the let's regroup it first. Let's regroup it first to avoid confusion. We are going to cancel out the 2 over here, then we are left with N, I bracket it out. Then I'm going to take the Avogadro number multiplied by the mass of one single gas molecule to be in another bracket. Then we have VRMS squared over here. Avogadro number multiplied by the mass of one gas molecule. This thing here just represents molar mass, because Avogadro number is how many molecules you have in 1 mole of gas. Okay, so you know how many gas molecules you have in 1 mole of gas. You multiply by each molecule, how massive is it? Then you get the mass of 1 mole of gas molecule. Mass of 1 mole of gas molecule is actually just the molar mass. So now you replace it with molar mass, and you can simplify it by cutting out the number of mole over here. Then your equation evolves to this state over here. Now you just bring the molar mass to the other side, you get 3RT divided by the molar mass, and you square root it, then you get your equation that relates between the root mean square speed and also the temperature. Okay, so this is the first equation that you can do to relate between root mean square speed and temperature. The next equation will be taking this KTR is equal to 3 over 2 KT. What you do is you replace KTR here with half mv squared. I replace it with half mv squared. Then from here you can remove the 2 from both sides of the equation, and you can shift the mass of one gas molecule to the right hand side. Once you square root it, you get the equation root mean square speed is equals to square root of 3 kT divided by small m. So you have 2 equations that relates between the root mean square speed and the temperature. The first equation here is usually for per mole situation, or you have molar situation in which you have the molar mass of the system. Okay, but for the second equation here is mostly focused on the per molecule case, or the molecular basis, in which here you're focusing using mass of one single gas molecule. So both equations will produce the same answer, but they are used in different contexts. Okay, so now we have fully derived a full circle over here. I believe that if you are using it for exercises or using it in the exam, you can't afford to remember everything, right? So here's a simplified version of the equation of the derivation we did earlier. First, you have the 2 equations that you derived through the 25 minutes video. Then you use your kinetic energy is equals to half mv squared to derive this equation that relate between pressure and translational kinetic energy. Then from there, you use your PV is equals nRT and PV is equals nKT to find the equation that relates between the total translational kinetic energy and the temperature, or the translational kinetic energy of one gas molecule with the temperature. Then lastly, you use back the kinetic energy equation to determine the relationship between the root mean square speed and also temperature. For this side, you have two different equations. They produce the same answer, but one is usually used for molar basis, and another one is usually used for molecular basis. So that wraps up the summary of how you derive all the equation necessary to relate between the macroscopic properties of gas and also the microscopic behavior of gas molecules.